What I'd like to do is get the session started. It's Capstone, Next Generation Disassembly Framework, with known on Quinn. So, sir, it's all yours.
Thank you. Hello. 1, 2, 3. Okay. So welcome to my talk, and in this talk, I will present a superior next generation disassembly framework named Capstone. And you can find the website for Capstone on the screen. And you can find there all the source code, documentation, tutorials, everything there. But what I will present today is what you cannot find from the website. That is the story behind the Capstone, the design of it, the implementation of it. That's those information you cannot find from the website. Okay, so here's my talk. First, I will introduce the current disassembly engines and their issues. And because all of them have many issues, so I need to come up with something that solves all the problems. And Capstone was born. And after that, I will introduce the ideas and the design behind Capstone. Next, I introduce the implementation in details. And after that, I introduce some very tricky x86 instructions. And some of them now as a engine can handle, but Capstone. And after that, there's some application built on top of Capstone because Capstone itself is a framework, it's not a tool. And conclusion. Okay, a quick slide on the story behind Capstone. So last year I did some binary analysis projects, and one of them I presented in the Black Hat last year. A tool for you to compile the ROP caches to build the shellcode. And at the time, OptiRope only worked for x86. So after that, I decided that, okay, I want to make it work for other platforms. So it's a change because now system and application and even everything moving towards multi-platforms. For example, Windows, previously they only work on x86, but now you can find Windows running on ARM, and soon I think ARM64, for example. So what I wanted is I wanted to find some disassembly framework for my project, because I need to reverse from binary to assembly. After that, my tool need to do analysis on that. So I want something that can disassemble x86 and ARM. The second requirement, I want something that run on Windows and Linux. A simple, two requirements, right? And finally, I want something that has friendly license. I don't want GPL. The reason is that GPL forced me to open my project with full source code. And I don't really want that. So I want something that non-GPL. But eventually, I could not find anything that meet all of these requirements. Even it looks, the requirement is very simple, right? But I could not find anything in last year, in 2013. And Capstone was born. And finally, Capstone does much more than what I wanted. Okay, the first part is I introduce all the available frameworks and their problems. Okay, we are looking at two major areas in computer security. First one is binary analysis. You can either reverse binary code to understand what it does inside. For example, you reverse a malware to understand what it works, to understand its internals. Or you can analyze the binary code to find vulnerabilities. Or you can debug some program. And in all of those cases, you have only machine code. You don't have source code. So the only choice, if you work in these areas, is that you need to work with assembly code. That's the only choice. The second area, software exploit. So you need to write exploitation for your bugs. You found some bugs and you need to write exploitation as well. And building shellcode is one important of this process, right? And you need to build shellcode, which means you need to write machine level shellcode. And also here you need to work with assembly code as well. There's no choice. Okay, so now looking at disassembled machine code. So the idea is that given binary code, only 10 bit, right? You need to decode and give it back the assembly code. First of all, on screen you can see on x86, given 101D8, you need to return 8 instructions, which 8 EBX to EX. That's on x86. On ARM thumb mode, given 1160, you need to return back store instruction, which store R1 register into some memory erased by R2, right? So you can see that disassembled machine code is a core part of all the binary analysis, reverse tune and debugger and exploit development. And you can see on the picture, all those tools have a common thing is that they have a disassembly engine at the bottom. That's a red layer on the screen. So all of them built on top of some engine like that. And in this talk, we look at the red layer on the screen. Okay, so the problem is that now we need to build some disassembly framework ourselves. What do we need to do? We need to have good understanding on hardware architectures and on all the instruction set of the hardware architecture. Second, we need to decode the binary code properly and return back the assembly, right? And that's not the end of the story. Because a good disassembly framework need to break down the assembly in details. So it can help the application to understand the internals of instruction. For example, a good disassembly must do this. That's the output of the Capstone. So first of all, you need to, given some binary code, you need to return the assembly code here. That's 8 instruction. But the good one should also return many other details. First of all, it gives back the prefix of this x86 instruction, the opcode, rex, the array size, mode RM, displacement, SIB in some case, in this case. And the engine should tell me that this instruction has 2 operands. The first one is here, the pointer to memory. The second one is the register, right? So it should tell me that the first operand is a memory type, which has a base EBX, which has an index EAX. And in this case, EX is multiple by 4, so the scale is 4. And the offset of this array is 2 here. And after that, it needs to tell me that the first operand has a size of 4 bytes. And so on. You can tell me the second operand is the register, which is EBX in this case. And this one also has 4 bytes in size. And that's not end yet. The good engine should tell me some semantic information. For example, it should tell me that this instruction modify E-flex register. So I put many requirements for a good engine like that. So here some quick slide for you to understand how to decode x86. So first of all, you need to have one instruction encoding like this. So first of all, here you can look and see that given one x86 instruction, you can see that the first 4 bytes is optional. And normally, you need to look at the primary opcode map to reverse to decode the instruction. If the first byte is 0F, the second byte is 0F, it might be 3D now instruction. If the first byte is 0F, the second byte is 38, that's another opcode map. If the first 2 bytes is 0F and 3A, that's another opcode map. So there's many opcode map and depend on the value of the bytes at the front. You look at the different opcode map to decode the input. So you can see that x86 is very, very complicated. Okay, we all know that building disassembly frameworks is very tedious. You need to spend a lot of time on understand the encoding schemes on the instruction set. And sometimes there are many instructions to deal with. For example, x86, the latest version, has over 1,300 instructions, and you need to understand all of them. And in some architecture, for example, like in x86, there are many corner case and many undocumented instructions. Still, you need to deal with all of them. You need to handle all of them. And in case you want multi-architecture, there are many architectures to care about. x86, ARM, ARM64, MIPS, PowerPC, Spark, and so on. And finally, to make your framework easy to use, you need to build binding for that. So people want Python, Ruby, Java, C#, JavaScript, and so on. So to have a good disassembly engine, you need to do all of those stuff. So it's very hard. So here's my demanding for a good framework, which I tried to look for last year. I want x86 and ARM. I want something that's actively maintained and updated with the latest change in every architectures in x86 and ARM, because x86 they extend the architecture very frequently, and that also happens with ARM. And if the framework doesn't update, it's not good. And again, I want multi-platform. Last year, I wanted Windows and Linux, and I developed my program in Python and Ruby, so I wanted Python and Ruby as binding languages. And again, as I explained, I don't want GPL. I want something more friendly, more permissive. But after I started to try to look for something like this, I understood finally that this is a long-standing issue of this industry, because there's nothing like this. Nothing meet all of those requirements, even in 2013, last year. To prove that, I have a slide. You can see. I show you all of the popular frameworks that a lot of programs are using now. So here I only list the most popular one: DStorm, B-Engine, UDIS86, and libopcode. Libopcode is actually very popular, but probably not many of you know. Libopcode is a framework running under all the GNU tools, GDB, ObjectDump, all of those GNU tools on Linux, on Unix, and so on are using libopcode. And you can see that for my first requirement, only libopcode support ARM, but the quality is pretty poor. They are wrong on many things, many simple instructions, and everything else only support x86. On my second requirement, libopcode looks, well, at least it supports ARM, but it doesn't work on Windows. So it's not good for me. For the third requirement on the languages binding, mostly nothing support Ruby, except there's one Ruby binding for DStorm, but it's very poor, and it's incomplete and it's unmaintained. Update, well, nothing update. Like there's some, you can find some framework on this screen. The last time they released, the last release was like 2 years ago. And the other framework, a lot of people submitted a pull request on GitHub, but the author didn't pick up. I think he disappeared or something. And on the last requirement, on the license, only B-Engine is good enough for me, because it is LGPL, which allow me to build commercial products on top of that without needing to open source my products. And UDIS 86 is not good because it is BSD license, which allow me to do everything I want. And on the other two frameworks, they use GPL, so it's bad for me because I need to open source my project. So you see many problems. Nothing works even in 2013. And given that this industry is very mature, you cannot find anything to meet those simple requirements. So I was really shocked to find that out last year. And The other problem is that apparently nobody wanted to step up to fix the issues. I didn't see anybody and any evidence on somebody try to fix the problem. And no hope is seen until Capstone came to rescue last year. Okay, next part I look at the Capstone and the design, the implementation. Okay, after that, I found that nothing worked. I need to decide what to do. So the easy choice that you can just sit still, relax, and wait for somebody to show up and solve all of your issues, all your problems. But I suspect that that might never happen. Nobody would solve my problems, and I would wait forever. So after that, I decided to take the problem in my own hand and solve all the issues once and for all. So I set out my goals for Capstone. First one, I want multi-arch. So I wanted x86 and ARM, but I wanted more than that because the other architecture are also very popular, like ARM64, which will become very popular in very near future. And also on MIPS and PowerPC because those architecture are very popular. I want multi-platforms. I want Windows, I want Mac, and I want Linux. For bindings, I want Ruby, Python, Java, and C#. I want some APIs that's clean, simple, intuitive, and doesn't depend on architectures. And to be a good framework, Capstone need to provide breakdown details on instruction. Need to break down instruction into details, and it also need to provide the semantic information. And finally, I want BSD license because I want to make it available for everybody to use without having to worry about the license. And all of those requirements are already eventually surpassed, as you can see later. Well, I set some goals for Capstone, but there are many problems. Multi-arch, too much work. So in the last slide, you can see I listed some available engines, and some of them has like 10 years of history, and it's still incomplete. Now we want multiple arch, not a single arch. Do you think how much time I spend on that? Maybe the rest of my life, right? Multi-platform, also a lot of work. Multi-bindings, too much work. You need to support all those bindings, and you need to be good on all of those languages to build the bindings for them. So do you think that it's possible to finish Capstone project in a few years with very limited resource? Why limited? Because Capstone started as a single man, my personal project, and much later when the project was public, committee started to contribute. So it was like personal project, and I can only spend my spare time on that. I don't work full time. I could only design and implement the Capstone in my free time. So that's the problem. But miracle happened because we made it. So here's the timeline. I started to design and implemented Capstone last August, and 3 months later, we called for beta test in public. And in December, we released the first version, 1.0 in the website. 1 month after that, we released 2.0. And the latest version is 2.1.2 was released in April this year. And the plan is to release the 3.0 version this month after I come back from Black Hat. And Capstone is getting widely and very quickly adopted by many important tools and trainings and works everywhere. And the package for Capstone is already available for all the important platforms like Windows, Mac OS, Linux, BSD, and so on. So here's the status of Capstone as 7 months old. Multi-arch, Capstone is second only to LibOpCode which support like 20 or 30 architectures. Because LibreCode like, has like 20 years of history of development behind. And Capstone cannot compare with that. On multi-platform, Capstone second to nobody. Because we support Capstone run on Windows natively, OS X, Linux, FreeBSD, OpenBSD, iOS, Android, and storage natively. Multi-binding, Capstone is second to none because we support 9 languages so far. Capstone provides more breakdown instruction details than anything else. Capstone is more updated than anything else. On maturity, Capstone is, I think, is pretty mature. It can handle more tricky x86 instructions than any others. And on documentation, there are a lot of articles on how to compile, how to install, how to customize, how to program Capstone. You can find that on the website. Okay, look at this picture. Compare Capstone with others. Multi-arch, only Capstone and LibreCode. Cross-platform, I suspect that only Capstone because the rest, I don't think they can compile on iOS or Android or so on. On instruction detail, you can see only Capstone, DStorm, and BA Engine. Update, I think only Capstone is updated. License, Capstone has BSD license, which is the best license you can find for open source. At the bottom, you can see the bindings, the list of the bindings of Capstone. We support Python, Ruby, C++, C#, Java, Node.js, which is JavaScript, Go, we even have Go bindings, OCaml, and Vala. And 3 of those bindings are maintained inside the project, and the rest was made by community. And you can see, you can compare with others. DStorm, another good one. They support Python and Ruby, but Ruby bindings pretty poor, Java and C#, and the rest only support Python. So we are pretty good on everything. So the next part is the design of Capstone. So the target is that I wanted to have all the design feature in under 1 year. I don't want to spend the rest of my life on this project. I don't want that. And given that I have very limited resource, so it might be like impossible dream, cannot complete in a very short time. Again, the problem is that too much work on multi-arch, too much work on multi-platform, too much work on multi-bindings. So again, do you think it's possible to finish in few months or even few years as a single man project? Maybe not. So my ambitions and ideas, I want everything, all the features in months, not years. How to do that? The only way is to stand on the shoulders of giants at the innocent phase and open source the project to get community involved and contributed. So who to stand on? I rely on the project name LVM, which is the open source project. On the compiler, you can find the rest at www.lvm.org. LVM is a set of frameworks for you to build compiler on. And inside LVM, you can find a set of modules for machine code representing, compiling, optimizing. And one thing that is very, very good about this project is that LVM is backed by many major companies in industry, by AMD, Apple, Google, Intel, IBM, ARM, AMG Tech, which is a creator of MIPS architectures, NVIDIA, Qualcomm, Samsung, and so on. And LVM has incredibly huge community around it. So everything about LVM is very nice. So here's a quick picture on the model of LVM. So like a typical compiler, it has 3 three main components: front end, optimizer, and back end. So the idea is that you fit in the source code to the front end, and front end will compile the source code into some intermediate language, and after that, intermediate language will be optimized by the mid-end component, and after that, the back end will compile again intermediate language to machine code. So that's the model of LVM. So the question is, why I choose LVM for Capstone? The reason is that LVM already supported many architectures. And because inside LVM they have a debugger, and to make debugger work, they need disassembly component inside, right? And which means inside LVM they already have disassembler internals. And you can find this is the LVM inside a component named machine code or MC. But the point is that MC is only usable for LVM modules, not for external code. You cannot write external code to use MC. And MC is closely designed and implemented by LVM. And it's very active and maintained and updated by a huge community and a lot of companies behind that. And finally, LVM is in BSD license, which is perfect, right? So my idea is that I fork LVM to build Capstone around MC component of LVM. And I only pick up only architectures that having disassembler, because LVM has many architectures, but not all of them support disassembler. And so far, LVM support 8 architectures. So Capstone also support 8 architectures. So you can see here on the screen, the diagram describes the architecture of the MC component. You can see that MC is the core layer of LVM, the yellow component. MC is used to integrate compiler with the internal assemblers. And MC is used by all the compilers, assemblers, disassembler, debugger, and Z compiler inside LVM. And MC is built around one big table of description or table gen in short. And this table gen describes all the machine instruction of every architecture. So every architecture has a very big table gen which describes all the instruction of that architecture. And after that, LVM uses one tool named LVM table gen to generate code from the table gen files. And the results, there are many .inc file for all the architectures. And those .inc files are used by assembler, disassembler, and code emitter from LVM. So the advantage of using MC, there are many. For example, first one, LVM has high quality code with a lot of tests done using many test cases inside LVM. So the code quality of LVM is very good. The disassembler inside LVM is maintained by top experts of all the architectures. For example, x86 mainly maintained and contributed by Intel, by the x86 creator. ARM and ARM64 maintained and contributed by ARM and Apple, which are who created the architecture and also the only device maker on the market now for ARM64. On the latest Apple device use ARM64. MIPS maintained by IMG Tech, which is somebody who created MIPS architectures. System Z maintained by IBM, also the creator of the System Z. Xcore maintained also by the company created itself. As an architecture, PowerPC and Spark are highly active, maintained by the community. So, if somebody want to write something compared with LVM, do you think it's possible? It's very hard, right? It's very tough to compare with those big companies, which means it's very hard to build better disassembler than LVM, which means it's very hard for you to come up with something that can be better than Capstone. The other thing is that new instruction and bug fix are fixed very frequently, very quickly inside LVM projects, which means if the bug is fixed, the new instruction is introduced, I can port it back to Capstone very quickly. So if you find some bugs in Capstone, you can either report to us or report to upstream to LVM projects. And once LVM fixes them, I can port it back to Capstone. So there are two ways. You can report to us or report to LVM. Well, the idea is nice, but there are many issues. First one, you cannot just reuse MC SE without a lot of effort. Why? Because inside LVM, the code is implemented using C++, but I want Capstone to use C. Because I want Capstone to be used by C program. If I use C++, C program is very hard to integrate with C program. But in a way, it's very easy for C++ code to use C. So C is the best choice. So I want C, not C++. So I cannot use MC as is. And inside MC, the code is mixed like spaghetti with a lot of MLVM layers. It's not cleanly separately. You cannot just take it out. If you want to take MC, you need to take a lot of things else together. So MC still works. So because the code is mixed like spaghetti inside. And the disassembly inside MC, they only give the output at assembly instruction. They don't have instruction details breakdown. So we need to build that ourselves. Another thing, LVM doesn't provide the semantic information for instruction like what you saw. So we need to do that ourselves too. And MC is not designed to be thread safe, which means you cannot build your program using MC. Just run like in parallel. This one is understandable because there's no need for code inside LVM to be multiprocessing. No need to be thread safe, so it's okay for them. It's not okay for me because I want to have a thread safe framework. And LVM doesn't have good Windows support, so that's a big problem. Okay, after you can fix MC to work for Capstone, you still need to build on the binding languages ourselves. And after that, once the upstream is updated, we need to keep up with the change in the upstream. So first of all, LVM fix something in the disassembler, I need to port it back. And that's also a big problem because we fork LVM. So we need to keep updating ourselves. So again, look at the picture, the MC layer. We fork LVM, but we don't take everything. Because if we take everything, that is, we take on the dependent layer of LVM, of MC. As a result, we take a lot of code. And a lot of code we don't really need. So we fork LVM, but we must remove everything that we don't need, right? So the point is where to make a cut. You need to get the yellow box out. But the yellow box out is not only yellow box out because if you get the yellow box out, you need to get a lot of other codes together out. So the yellow box still works. So the point is where to make the cut. So I decided that to make a cut inside the yellow box. The question is that if you cut too little, the result is that you get a lot of redundant code, which you don't really need, because there are a lot of code for compiler, for code generator, for assembler, for many other things we don't really need for this assembler. So cut too little is not good. If you cut too much, it would change the code structure, which make it very hard to keep update with the upstream. Because if you change a lot, once the upstream LVM change, you need to port it back and you need to fix a lot of things. So you cannot cut too much, you cannot cut too little. So after a lot of time to look at the LVM source code, I came up with some, I think, optimal design for Capstone. So I just take a disassembly component inside MC and make very minimal change. Because after that, I can still easily keep updated with the upstream. And I only re-implemented only require dependent layer ourselves. Okay, so on this screen, you can see the diagram describes the core component of MC. I remove everything else that's not relevant. So you can see that given the input on the left side, some binary, the input will go through the one component called disassembler. This component will decode the binary to some internal information of that instruction. And after this decode step, the output will be sent to the printer, which will print out the internal information of the decoded instruction to a buffer. And inside the buffer, you have the assembly. So given the input on the left side, you get the output on the right side, the assembly. Represent the binary code. And these two components, these two main components, disassembler and printer, they rely on many small other components at the bottom. So the question is what to do. So the design of LVM at this step is that I build the core of LVM around these two components, disassembler and printer, with very minimal change. Because these two components sometimes are updated. For example, when some architecture they add new instruction, add new feature, they update these two components. So I decided to keep these two components almost as is with very little change. But on the dependent layer at the bottom, they don't change very often or don't change at all. So I rewrote all of them, all of the bottom layers. But the top layer, I keep them almost as is with very little change. And because you remember that LVM code is in C++, right? So I need to replace all the C++ code with C code. So I need to rewrite a lot of things here. And remember the table gen tool, which produce C++ code for .inc file to be used by disassembler. So I also fork this tool, table gen. But this tool now produce pure C code, not C++, because the original table gen give you the C++ code, which I cannot use. So I fork table gen and my table gen produce pure C code. Okay, so after this stage, we have given the input, you have the assembly as output, right? But that's not enough because we still need to provide the instruction details to break instruction into many details, right? So how to do that? What I did is that I hook into the printer layer, and my hook will build the instruction details for me, and the hook my code will put on the details of instruction into the structure named CS underscore INSN, and in this layer, my hook go in give all the details like instruction ID, the size of instruction, the mnemonic, the operand strings, and after that, it produce all the operands information, how many operands of this instruction, and the type of each operand. It can be immediate, it can be register or memory. And finally, my hook into this layer will give out the architecture dependent information for each architecture. It can be like prefix, mode RM, SIB, etc. for x86 and so on. And the next part I had to do is that I need to isolate some global variables inside MC to make Capstone really thread safe. The next part I had to do is that we want semantic information, right? You want to know which register this instruction read, which register this instruction modify. You want to know which groups this instruction belong to. So for example, you can see here, for example, the iMoon instruction, it modify, no, yeah, it use AL register. And after that, as output, it modify AL, eFlex, and AX. There's an example. This instruction CVTSD2SS belong to SSE2 instruction group, instruction set. So I need to expose all of this information for Capstone. And the point is that LVM originally don't provide you those information. So where I took this information from. So the idea is that in the TD file which I presented in the first few slides, the TD file has all those semantic information for the compiler. The compiler uses those information for code generator, but the assembler, the disassembler inside LVM don't really use them. But I think that those information can be useful. So my idea is that I took this information out and give it to Capstone. Those information originally not for disassembler, but for code generator inside the compiler. So the idea is that I extract all of this information and put them in many mapping tables inside Capstone, and at runtime, at the hooking layer, at the printer layer, I copy all of this information into CS, INS, and structure. Okay, let's take a look at this structure, which keep all the information of the disassembly instruction. So here you can see that I group the information into two groups. The first one is architecture independent. You can see this box, the yellow box, and this box are all architecture independent information. Because all the information has ID, instruction ID, has arrest, has a size, has the bytes, how many bytes, all the bytes that instruction contain, the mnemonics, operand strings, and the pointer. This pointer point to the next block, and all the instruction has information like which register this instruction read, which register this instruction modify, and which groups this instruction belong to, right? And at the bottom, there are architecture dependent information. Okay, and you can see that Capstone is superior to LVM, disassembler, because it's independent. It's built around LVM, but it's much better because it's independent framework. So you can build your tool on that. It's very small. It provides much more information. It's thread safe. You can embed Capstone inside firmware OS. It's more malware resistant because LVM, the disassembler inside LVM is not really resistant to many x86 malware tricks. And it has actually support more hardware mode and more instruction sets than LVM. You can find more information at the link at the bottom. Okay, so the bonus of Capstone is that we cannot always rely on LVM to fix bugs because this assembler inside LVM is still considered second class, and sometimes LVM developers they don't want to fix it. For example, if the code is not generated by the compiler, they don't fix it. So there are some very tricky bugs, tricky instruction that the compiler doesn't produce. So the disassembler inside LVM doesn't understand it, and because those instructions are never produced by the compiler, so the LVM developers they don't want to fix the disassembler, right? But because we care about this, because we want to use Capstone for malware analysis, so we need to fix all of them ourselves. We cannot rely on LVM. Here's some cheeky injection. You can see that Capstone can handle all of them, and compared to others, nothing can handle all of them. Even a very good tool like IDA, they still miss some injection. Okay, there you can find many tutorials on how to write application with Capstone on the website. I skip because I don't have much time left. And so far, already many applications built on the internet using Capstone you can find here. And many of them, they switch from something they used before to Capstone because thanks to that, their application suddenly support many architectures. Okay, there's some tool I built myself and to introduce. First one, cheater bot. You can send a cheat to the cheater bot named Cbot as this, like this. You specify the architecture. Like this guy you want to disassemble the 32-bit or x86, and after that you send the binary in hex code. And after that, in 1 second, the bot will return back the assembly. So you can send your question to this cheater bot, and in 1 second you get back the result. The other one, which I launched last week, is a tool named Cinema. You can find that at that address. So I have a quick demo here: www.cinema.org. So basically, this tool let you type the input as a hex code in this box, and you choose the architecture at the top. After that, you submit. For example, you want to decode something like this. So just paste it here. You can see the format can be very flexible as long as it contains hex code inside. And after that, you choose, for example, in this case is 64-bit Intel, and submit. See, you get back the assembly. And the good thing is that if you move the mouse on top, you can see all the detailed information of every instruction. Like this. This one modify a flag register, right? And another thing, if you click into this instruction, it can link you to the assembly manual. So it's can be very handy for you want to decode something. So just use Cinema because it's already open to the public at that address. Another tool which I'm trying to build now, still work in progress. I'm trying to build a framework named Epic, which can translate binaries from all the architecture on the left side to LVM. And on the right side, you have LVM bitcode as the output. And after you have the LVM bitcode on the right side, you can use many existing binary assist tools using LVM. So you can do binary analysis with all those architecture on the left side. One more slide. Capstone future is guaranteed because we rely on LVM, right? So you can see that some architecture they continuously update their instruction sets, and they add instruction very frequently. For example, here's the timeline of SMD in Intel architectures. And it doesn't stop here because next year, Intel will add one new instruction set named AVX 512, which will be out in some real hardware next year. But Intel already took care of that. Intel already supported AVX 512 in LVM. And as a result, Capstone already have that. So you can see that the future of Capstone is guaranteed. conclusion, Capstone is a very good framework, multi-arch, multi-platform, multi-bindings, very nice API, very simple and easy to use. It provides details and semantics on instructions. Rich choice of option to customize the engine at the runtime. You can find many documentation on the website. It can be easily embedded inside the firmware OS. Features granted, and the license is BSD, very, very free, very open. And we want to say that we are seriously committed to this project to make it the best engine for community. So you can be sure that Capstone will be around for a very long time. And in the future, we want to try to build a lot of applications on top of Capstone very soon. We might talk about that in the future. So here's on the link, the website. You can get the source code from GitHub with a lot of documentation. You can find the information on the Jitterbot. And if you need that, that's using my that website. It's already out, open, free. My thanks to the community, to the contributors, to the binding authors, and some people who helped me on this project and on these slides. Any questions? We're running out of time.